So after the break, I hope you would feel more refreshed. The reason is that we are going to talk about a very important concept. It is called resting membrane potential. We learned about resting membrane potential before the break. We learned that scientists use a voltmeter to record the neuron so that they find out that the resting membrane potential of a neuron is minus 70 millivolt. But exactly what happened inside a neuron that generate this negative voltage? So we are gonna explain it to you how. It is a very important concept. Why is it so important? Let me give you an example. When I was a graduate student at USC, I was a TA for different classes. One semester I was a TA for physiology class. And then one of the students told me that he had learned about the resting membrane potential and action potential 3 different times from 3 different classes. And he told me that he learned the first time about resting membrane potential and action potential from lower division introduction to neuroscience. It is a GE class for non-major student. So the first time he learned about it from this class. Second time he learned about this from upper division neurobiology class. And when he took physiology, it was his third time to learn about resting membrane potential and action potential. So if USC teaches student the concept about resting membrane potential and action potential in 3 different times from 3 different classes, that means they are very, very important concepts. So I want you to pay attention to it. And if it is the first time you learn about this, and if you don't understand, that is totally normal, okay? Even USC, they have to teach it 3 different times. So if you don't understand it, feel free to ask me about it on Thursday. And or you can go to the biology collaborative learning center there to ask Dr. Misuno or Professor Beeman during their office hour there. They are very good at explaining this concept to you. So let's start. So of course, we first have a cell. Okay, this is a cell. It sounds very, it looks very generic, yes. Okay, remember what we talked about, the concentration of ion inside and outside of the cell. Okay, for sodium, sodium ion has a very high concentration outside of the cell, but it has a very low concentration. See, it is so small, okay? Low concentration inside the cell. For potassium is different. It's the opposite. Potassium has a very low concentration outside of the cell, but a very high concentration inside the cell. Okay? And then chloride. We just learned about this before the break. I hope you still remember. Chloride has a very high concentration outside of the cell, but it has a very low concentration inside of the cell. Okay, is that clear? Now we set it up like this. Then let's talk about potassium first. Well, in a neuron, we have something called lead channel. Lead channels, they are membrane protein, and as you know that, okay, channel meaning that they allow ions to go through. So the blue one here is the potassium lead channel. So it allows potassium to go through. And most of the neurons, they have a lot of potassium lead channel. And this potassium lead channel, they open all the time. So in other words, potassium can go in and out freely. Okay, it's not one-way opening. It is potassium can go through it freely. So the question to you is that under normal situation, which direction of potassium will go through the lead channel? You have two choices: from outside the cell to go into inside the cell, or from inside the cell to go outside the cell. Well, I hope you make your choice. I hope most of you will say that from inside the cell to go outside the cell, because inside the cell we have high potassium ion inside the cell. Outside the cell we have low potassium ion outside the cell. So potassium ion will go like this, will go outside the cell. Okay, we call this what? What do we call this? Is it simple diffusion? No, it should be called facilitated diffusion because it uses protein, membrane protein. So potassium normally will go from inside to outside by facilitated diffusion. But as it goes outside, it won't go very far away, okay? Because diffusion does not need energy, so it will just go outside, and then all the potassium ion will deposit on the cell membrane near, okay, they won't go far away because they don't have the ATP energy to drive them to move away, so they will just move out of the cell in a short distance, and then they just sit on the cell membrane. So as you know that when you do this, oh, by the way, we call this of course this is called facilitated diffusion, but there's a better name. We call it potassium is moving down is chemical gradient. Chemical gradient. So the chemical gradient will let the potassium go from inside the cell to outside the cell, okay? Now, when there are lots of potassium ion deposited on the outside the membrane, and potassium ions, they are positively charged. So what will happen next? Positive charge will attract negative charge because it is opposite charge attract, okay? I don't want to use green chloride because other than chloride you can have other negative charge. So I would use let's say orange. Okay, you can have a negative charge. It can be any negative charge like chloride or fluoride. All kinds of negative charge will be attracted to on the inner surface of the cell membrane. When it happens, when you have a lot of negative charge in the inner surface of the membrane, what will happen? Well, as you know, the opposite charge attract, then the potassium ion, because they are very close to the membrane, they would want to go back. So potassium like this, they want to go back to meet with the negative charge. We call the opposite charge attract, we call this electrical gradient. I'll give you an analogy. High school romance, okay? Remember, you may or may not have this experience, okay, but at least you should have watched this on movie, from the movie or on the TV, okay? So high school kids, they are, well, as you know, they are very horny, you know, they have all kinds of high hormone level in the body. So the high school guy misses his high school sweetheart, so what does he do? At night, he went to her house, and then he throws a pebble to so-called knock on her window, and then she opened her window, and then she saw that, oh, he is here to visit her, and then of course he will not be satisfied just seeing her on the window. So the guy, high school kid, will climb the tree or climb the wall to go to the window, go to her window, and as you know, he will not satisfy to just to see her on the tree or at her window. So he will actually go through her window to go to see her. And as you know, when he goes into her bedroom, he will not just say, okay, good night, and then she will climb out from the window and then go home, and he will probably stay in her bedroom, and then they will do something called, you know, recombination, and then next morning he'll leave, and then 3 to 4 months later they will be in a big trouble. Well, you probably know what happened. And then, so this is the scenario, okay? Potassium ion, they are the high school guy. Potassium ions, they are the high school guys, okay? They are here outside the house of the high school girl, minus charge. The minus charge is the high school girl. So what happened is that, of course, the high school guy will not be satisfied. That's why when the high school girl, the negative charge here, these negative charge, when they are at the window, like the channel, it will attract the high school guy to go through the window. To attract the high school guy to go through the window to meet with her. So this is what happened. Yes. And as you can imagine, okay, potassium ion is going out of the cell all the time, and at the same time they are coming back in to the cell. So one goes out, one goes in, and then eventually they will be at the equilibrium. So the chemical gradient and electrical gradient, they will reach an equilibrium. We call it dynamic equilibrium. The dynamic equilibrium, meaning that the ion, they are still going in and out. Okay, it's not like, okay, equilibrium doesn't mean that the ion stop moving. The ion does not stop moving. The ion keeps on moving in and out. it goes out because of the chemical gradient. It comes back in because of the electrical gradient. The opposite charge attract. It's like the opposite sex, opposite gender attract. So so we call it dynamic equilibrium. Okay, so the ions, they are moving. It's just that, okay, the push forces and the push force and the pull force, they are in balance. Then what happened? When the chemical gradient and electrical gradient, they are at dynamic equilibrium, what do we call that? We call this equilibrium potential. So potassium reaches something called equilibrium potential. We call this, let's do it in blue. We call this EK. When potassium reaches the dynamic equilibrium or the equilibrium potential, EK value is minus 90 millivolt. This is something that I want you to memorize, okay? Okay, now, next. Remember we have sodium. Sodium also has sodium leak channel. Okay? Sodium will do similar thing, but it will be opposite. Why? As you know, that sodium has a high concentration outside, lower concentration inside. So what will happen? Sodium will have a tendency to go from outside to inside. But as the potassium, it won't go farther away. You only stay at the inner you'll stay at the membrane inside of the cell. Okay. And then as it happens, of course, it will attract the opposite charge. It will attract negative charge deposited outside of the membrane. And that is the high school analogy, if you remember high school analogy. And then sodium will actually go out to meet with the negative charge. So in here, the first one here, this is the chemical gradient. When it go outside, this is the electrical gradient. So same thing, when the chemical gradient and the of the sodium ion and the electrical gradient of the sodium ion reach the dynamic equilibrium, we call this ENA. And ENA is approximately equal to So ENA is approximately equal to plus 60 millivolt. Again, I want you to memorize this. Memorize this, and then same thing happen for the chloride channel, leak channel of chloride. Okay, we have a higher concentration outside, so chloride will go into the cell. Then you have the negative charge of the chloride ion inside the membrane. Okay, and then you will attract the positive charge. Let's say the positive charge is purple. You attract positive charge outside of the membrane. In this case, chloride will try to go out to meet with the positive charge, the high school Romance analogy. Okay, so as you can see that this is the chemical gradient, and this is the electrical gradient. Okay, now when the chemical gradient of the chloride ion is at the dynamic equilibrium with the electrical gradient, we will have the ECl. The equilibrium potential of chloride is approximately minus 70 millivolt. Again, I want you to memorize this. Okay, I want you to memorize these three values. It is important. And then, so I still haven't explained to you why we will have these three here. So in the next slides, I'll talk about why. In the previous slides, you know how the what happened in the cell and the ion. You know, when there is when the cell is in the resting membrane potential. But we only talk about the movement of each ion. We haven't talked about how each ion contribute to the formation of the resting membrane potential. So here is the here's my explanation. Okay. So let's see. Wait. Point. Okay. So when the electrochemical gradient of an ion reaches is dynamic equilibrium this ion is at its equilibrium is called this equilibrium potential. Equilibrium potential. We call it E ion. And equilibrium potential can be calculated by something called Nernst equation. Okay, Nernst equation. So Nernst equation is basically a constant multiplied by the natural log okay, it is the bracket means concentration of the ion outside of the cell, that means extracellular, and then concentration of the ion intracellularly. We can simplify the Nernst equation into this one, 61.5, and take the regular log, and then we still do this. Our extracellular ion concentration divided by the intracellular ion concentration. The good news is that you don't need to memorize this equation. I will not test you in the exam. But what I want you to know is that the equilibrium potential is equilibrium potential depends on what? It depends on the concentration of that ion extracellularly and concentration of the ion intracellularly. This is very important. So why is that? Well, let me give you a real life example. How many of you have watched the movie Kill Bill? Especially the second one, the second Kill Bill. At the beginning of the second Kill Bill, remember Daryl Hannah disguised to be a nurse, and she is going into Uma Thurman's room in the hospital, because Uma Thurman at that time she was unconscious, is in comatose, and then Daryl Hannah, what did Daryl Hannah wants to do? Daryl Hannah wanted to inject potassium chloride into the IV line of Uma Thurman. Why? Because Daryl Hannah wants to kill Uma Thurman. So how come injecting potassium chloride can kill someone? Well, if you remember what we talked about, the concentration of the relative concentration. So the concentration inside the cell, we have very low sodium, and the concentration outside the cell, we have very high sodium. What about potassium? Potassium is of the opposite. Concentration inside the cell, we have very high potassium, but concentration outside the cell, you have very low potassium. So if Daryl Hannah succeed to inject potassium chloride into the IV line of Uma Thurman, then the extracellular fluid will have a very high concentration of potassium ion. And based on the Nernst equation, if inside of the cell you have high potassium ion and outside of the cell you also have high potassium ion, what will happen? You will change your equilibrium potential of the potassium. When you change the equilibrium potential of the potassium, guess what? you will also change the resting membrane potential, and then basically you will shut down the entire nervous system. I'll further explain it when we talk more about how the ion contribute to the resting membrane potential. Now let's move on to the next few one. So what does it mean when an ion reaches its equilibrium potential? What does it mean? When an ion is at its ion equilibrium potential, or the leak channel of that ion. So we call this leak channel ion. Open. So that's the physical meaning of the equilibrium potential. Previously we said that okay, when the electrochemical gradient they are at the dynamic equilibrium, then it is at the equilibrium potential. Now what the physical meaning is that when an ion is at equilibrium potential, then all the leak channels are open. Okay. So what happened? Think about this. When let's see if you still remember. Let's see if your short-term memory is good. What is EK? EK is minus 90 millivolt. What happened? During resting membrane potential? At resting membrane potential, which is equal to minus 70 millivolt, what happened? Because resting membrane potential is minus 70 millivolt, it is very, very close to minus 90 millivolt. That's why at resting membrane potential, most of the potassium leak channels are open. What about sodium? What is ENA? See if your short-term memory is good. ENA is approximately plus 60 millivolt. So at resting membrane potential, which is equal to minus 70 millivolt, then what will happen? Only a few leak channel of sodium. Well, I'm running out of space. You can put it open. So the reason is that the equilibrium potential of sodium is plus 60, which is far, far away from minus 70. So we will only have maybe one or two sodium leak channel are open. Last but not least, what about chloride? What is the equilibrium potential of chloride? It is minus 70, okay, millivolt. And then same thing at RMP minus. So at resting membrane potential, theoretically all the leak channel of chloride, they are open. Well, I'm running out of space, but I want to write are open theoretically. But guess what? You may think that, well, if it is the case, that means at resting membrane potential, chloride should be the one that contribute the most for the resting membrane potential. Is it true? No. The truth is that actually it is the potassium leak channel or the potassium leak current. They are the one that contribute the most to the resting membrane potential. Let's talk about it in the next slide. So how come potassium is the one that contribute the most, not the chloride? For this we have to talk about something called a permeability. Permeability is basically you can simplify, or I can give you a simplified definition. It means that how easy how easy an ion go through a membrane. This is a very simplified definition. How easy an ion go through a membrane. So it depends on two factors. One, number of channels of that ion, and second one, number of opened channels. So permeability depends on at least these two factors. Okay, take a guess. What is the permeability of the free ion? So permeability, the symbol is basically capital P. It is the symbol. So the permeability of different ion is basically permeability of potassium versus permeability of chloride versus permeability of sodium. Take a guess. So the permeability of potassium, well, let's color code it just to be consistent. Permeability of potassium, let's assume it is 1. And then the permeability of the chloride will be approximately 1/2. Approximately, okay? It is actually around 0.45. 0.45 should be the correct number, but I round it off to 1/2 so that it is easier for you to estimate. And then sodium is approximately 1/20th. The exact number is approximately 0.04. 0.04. So you can see that the highest permeability of the three ion is actually potassium. Because potassium has the highest permeability, so potassium is the one that contributes the most to the resting membrane potential. You may say that, okay, you still haven't talked about how, Well, you know that Nernst equation is for determining the equilibrium potential of each ion. Okay, how do we determine the resting membrane potential from all the ion together? It's not just we add them all together. No, it's not that simple. We have something called a Goldman equation. Goldman equation is the equation that, well, let me show it to you. It finds out the membrane potential Vm as 61 multiplied by the log of permeability of the potassium ion multiplied by the concentration of the potassium ion outside of the cell, and then pK multiplied by the concentration of potassium inside of the cell, and then you add PNA, which is the concentration of the sodium ion outside of the cell, multiplied by the permeability, and then you have the sodium ion inside of the cell. And then the last one is a little bit tricky because you understand why. The permeability of chloride ion multiplied by the concentration of chloride ion inside of the cell. So basically, the Goldman equation takes into an account of the permeability of each ion and also the concentration of each ion extracellularly and intracellularly. So when it takes into account of the permeability and the concentration, then everything together, you will get the what we call the resting membrane potential. So the key point, resting membrane potential is mainly determined by potassium, the lead channel of potassium, but the lead channel of sodium and lead channel of chloride are also involved. Okay. Let me see if I miss anything. Okay, I think that's pretty much it. Okay, yeah, that's it for tonight.